Today we will be talking about ultra-wideband based physical layer key sharing for body area network devices. This paper was written by Dutliff, Boshoff, Morgana, Zhou, Raphael, Nkrow, Bruno, Silva, and Gerhard Hancke. And we are all with City University of Hong Kong. Our paper describes how we can ensure efficient and secure cryptographic key sharing in body area network devices with an integrated ultra-wideband antenna. These wearables often have limited computational ability and therefore cannot execute our current cryptographic key sharing algorithms. Alright, so the first thing that I'm going to do is introduce everybody to the hardware that we're using. As you can see, we have two Decawave ultra-wideband modules. We have one attached to my arm, which is going to represent your smartwatch, and then I've got another one which is going to go in my pocket, which will represent a smartphone. Now, during our actual experiment, we had two additional locations. We had one device attached to my chest and then another one attached to my head. And now the two devices are going to communicate with each other. They are antennas, so they can send ultra-wideband signals. And at each device, we can record the channel impulse response. Now, the channel impulse response tells us how a signal is propagated by the environment. And so as soon as I move somewhere, the channel response also changes. But the crucial thing is that due to the electromagnetic reciprocity theorem, the channel impulse response recorded by both devices are the same. Now I'm just briefly going to show you our first environment that we used for recording, and it's this long corridor with some metal lockers. Alright, so this is the second environment in which we did our testing. As you can see, it is quite a wide open environment, so that allows for different types of channel impulse response, and it also allowed me to walk around quite a bit. And now in each environment, we had two different types of valid testing scenarios where I was either dynamic as a person and could be moving around, or I was static and had to either stand still or sit down. And this was really to emulate different types of postures that a person would be in during their daily lives. Now, we also had one final test where we had to test the security of our system, and this is where we would have an attacker placing a snooping antenna on a person's body as close to my arm as possible, so that the attacker can record channel impulse responses as close to a legitimate one as possible. So after Alice and Bob have sampled a valid channel impulse response, they use M-array quantization to extract a cryptographic key and then use compressive sensing to reconcile any differences between their two keys. Finally, we can look at our results, which shows that any two valid devices on a person's body can share a key with often over a 90% key success rate, while attacker keys look completely different. Thank you for watching my video, and thank you to the IES Student and Young Professional Paper Assistance Program.